So what I want to consider in this first part of the course is player controls. I want to consider the input for the player so that we can move the character around the level. We began to implement this functionality in the previous part of the course, but now we need to consider it in more depth. So to begin, let me just press play on the toolbar, and you can see that we have our character in the scene here. And here we have the character node in the hierarchy panel. If I just expand that node, you can see that I've positioned the camera object as a child of the character so that it follows them as they move through the level. Now right now, if I press the W key on the keyboard, we can move the character forwards by 1 increment. That is by 2 world units. And the idea is so that we can constrain player movement to the tiles on the floor. Now of course the player hasn't been aligned right now to the correct starting position, so they're not quite as I want them. But if I want to turn the character to walk to the right hand side, for example, or to turn them to move to the left, or even to turn them all the way around and move backwards, I can't do that right now because I have no rotation controls. When I press the A and the D keys on the keyboard, I want to turn the player so they can face a new direction. So we need to implement some rotation controls into here. So I'm going to be tweaking the controls that we have created. We have here in the Assets and Scripts panel, we have the Player Controller script that you can see here in the Object Inspector, and I can also load that here into MonoDevelop, and we have the Player Controller.c# file, which we created in the previous section of the course, and that implements the basic movement controls that we have already. But it's still not enough. It's still not quite what we want. So what I'm going to do now is I'm going to jump back into the MonoDevelop and begin to tweak and change the player controller file to support the character movement that we need. So I'm here in MonoDevelop looking at the player controller.c# file, and what I want to do here is to explain to you some of the changes in the code that I've made to get movement up and running for our player character here. So as we've seen before, we have this basic enumeration at the top of our file, enum for movement here, and it's a C# enumeration which just defines the different states of animation for the player character. And when I scroll down, you can see we have our player state variable, which really defines the current state that the player is in, and there is the animcomp.setInteger statement that we've seen before to actually pass values directly to the mechanim animation graph to control which state is playing. We've seen all of that before, but what I want to pay particular attention to is a new coroutine that I've added here for rotation, which you can see here is called rotate, and it will rotate the character a specified number of degrees around their y-axis. So let me just minimize MonoDevelop here and return to our level. Let's just consider the kind of controls that we need. Because we want to restrict player movement to our general grid that we have here, this horizontal and vertical grid, we want to make sure that the player can only rotate by 90 degrees. So for example, if they move here and they want to turn down here, for example, then we have to rotate them exactly 90 degrees so they can continue along their path in this direction. So it's important to constrain player rotation to 90 degrees. Now to achieve that, if I just bring back MonoDevelop, you will see here that I've added rot increment, and the default value is 90 degrees, and indeed I want to keep it at that. This defines the amount of rotation in degrees that the player should turn on the y-axis when we want to turn to change direction. So if I just minimize MonoDevelop and I scroll up in the hierarchy panel and I select the player character, you can see here in the object inspector for the player controller component that we have rot increment, and it's set to 90 degrees. I also have a property rot time, which determines the amount of time in seconds that it should take the player to rotate 90 degrees. In this case, I specified a value of 0.5, which is half a second. And here we also have move time, which represents the amount of time, again in seconds, that it takes the player to walk forwards by 2 world units. And again here I've specified 0.8, so that is 80% of a second. So I'm just going to bring back MonoDevelop again and take a look at the rotate coroutine that I have added to this source file here. So in this movie, what I want to do is to consider the rotate coroutine that we've coded for the player controller C# file. I'm just going to scroll down. Now it's important, the purpose of this rotate coroutine, when I can find it, there it is at line 68. The purpose of the rotate coroutine is to rotate the player character around the y-axis. It's very similar in fact to the move function because it uses exactly the same logic. It transitions the position or the state of a player from one moment to the next over the rot time in the case of rotation. So for the rotate coroutine, what we do is we begin by getting the Y rotation, the current Y rotation for the player character, using the transform component rotation.eulerangles.y. That gives us the rotation for the player character on the Y axis. And then we calculate the destination rotation that we want to rotate to, which is the current rotation of the player plus the rotation increment, which will be either 90 degrees or negative 90 degrees. This rotate coroutine is called inside the handle input function, which is called every frame to update player input. If I just scroll down to the handle input function, you can see here at the bottom we check player input. If they're pressing the A key on the keyboard, the left key, then we rotate by negative 90. And if they're pressing the right key, which for me is the D key, then we rotate by positive 90 degrees. So I'm going to scroll back up to the rotate coroutine that we have here. And so we calculate the destination rotation that is, and then over the rot time, which is specified here, and for us this is going to be 0.5 seconds, then over that time we interpolate the angle so the player rotates from their current orientation to the destination. And so finally here at this stage the rotation is completed. So what I'm going to do now is, with all this code integrated together, I'm going to give it a test in the editor. Remember, if you want to check anything in this source file, it is included in the course companion files inside the playercontroller.c# file. So just open up the Unity project and open up that file and you'll get where you'll need to be. So I'm just going to minimize MonoDevelop now and switch back to the Unity editor and see this code in action. So if I press play on the toolbar and I press the W key on the keyboard, the player walks forwards. And if I press the D key, we rotate to the right. If I press the A key, we rotate to the left. And again, W key moves forwards in the direction that we're looking because we're moving forwards along the forward vector. So again, I can turn left and I can walk forwards. And again, walk forwards along this way, rotate this way. And so we've got this sort of player control set up here and it's looking pretty good. But of course, right now the player is not properly constrained to the main game grid. If I just stop playback for a moment and switch to the scene tab, you can see here in the scene, let's just switch to a perspective view, like so. You can see here on the floor, if I select these pieces, we've got one floor tile here and another floor tile here. And the player really is sort of in a nowhere place between them. We want the player to be constrained to these floor tiles in a nice, neat grid. So I'm just going to position the player now to a proper starting position. Let's just switch to an orthographic view, maximize the game viewport. Actually, let's just select the player character first. And I'm going to position the player to about here. I'm just going to try and line up their transform gizmo to around about the center of the tile here. So now let's just switch back here to perspective view, and I think that's looking fine. Let's just press play on the toolbar, and again now the player is constrained to the level grid in nice neat increments. So you can see that he's moving from one tile to the next tile to the next tile and the next one, and we rotate and we're also constrained to the grid because these are nice neat squares measured 2 by 2 weld units. So that's how, using the move and the rotate function, we can create basic player controls. Next, we're going to be considering adding boxes and collision detection. So stay tuned. So now I want to introduce the crate or the boxes into the level. These are the boxes that the player is going to be pushing as they move around the level, pushing onto their destinations, that is. So the crates really are a critical part of this box pushing game. So we can find these inside the meshes folder. They were already imported in the first part of this course. So you can double click the meshes folder and you'll find them inside the props folder. Here, when I can select this box object, here is the crate object we're going to be using. In the preview panel, it's presented in a nice bright purple color. So what I'm going to do is drag and drop this box into the scene so you can see it here. And again, it still appears at this bright purple, but we can easily fix that by applying a texture to it. Now, the first thing you'll notice over here in the object inspector is that this cube, this box object, has an animator component. Now, we are not going to be playing any animations at all on this box, or, well, we are going to be animating the box in the sense that the player can push it and move it around the level, but we're not going to be playing any animation data on it using the mechanim system. So we can remove this animator component completely, and indeed in cases where you don't need any animation at all, I recommend that you remove the animator component from your object. So I'm going to just click on this cog here and choose remove component, and now bam, it's gone. So I'm going to switch over to the materials folder, which you can see here, and the material data for the crate here is not in fact on the prop material, it's on the environment material. So I'm going to drag and drop that onto the crate, and now you can see we've got the texture data applied. And I'm just going to kind of align this, just maximize the viewport here, and use this transform grid to align this cube to roughly the center of the floor tile. So around about there should be fine, like so. So I'm going to arrange it about there. Now, the first thing you'll notice here is that perhaps the crate is a bit too small, and in fact it's penetrating through the floor. So we want to just raise this up in the scene here, like so. But it's pretty small, and again we want it to be a little bit larger. So I'm just going to increase the scale on all axes to about 1.5. That should be around about enough. So just raise that cube up onto the floor there. And I think that's looking about right. So that's about the right size for the crate and for the rest that we're going to be using. In general, I'm going to be creating only one crate because we're going to be adding some extra data to this, and I'm going to be creating a prefab from this crate so that all the other crates will simply be instances of that prefab. So you'll see that we've now got a crate in the scene, but if I press play on the toolbar, we've got a problem. First of all, we've got a player character that can just walk through crates. So although I'm walking forwards here, the character is not pushing the crate. But not only that, we've got a character that can also walk through the walls in the level. So long as he's constrained to the grid, he's just walking through the walls. And that really is not what we want. We need to get some proper physics and collision detection in here. So that's an issue that I'm going to be turning to next. Now I want to consider the issue of collision detection. In Unity, whenever we need to detect collisions between any two objects, we need to use collider components. That's the way that Unity handles collision detection. Now there are two main ways we can get collider components onto our objects. One way, for example, if we wanted to get colliders onto the scene environment geometry here, is to go over here to the project panel where it says Assets, Meshes and Environment. We could select any object, for example this corner piece. And again in the preview panel you'll see that this object is rendered in a bright purple color because it cannot find the appropriate material. But let's not worry about that right now. Over here in the Object Inspector under the Model tab, you will see if we move down the Generate Colliders checkbox. And if we enable that and scroll down and click Apply, Unity will search through the geometry of this mesh and generate colliders dedicated for that mesh. And we could repeat that procedure for all of the others, and that would automatically add collider components to them. But that is a very expensive way, computationally expensive, for generating colliders. It can lead to performance problems. Now a much more optimized way would be to use the file menu at the top here and choose component and then choose, for example, physics, and use a box collider to simply approximate the scene geometry. That is a much more optimized way, and it's the method that we're going to be using here in this course. Now I do want to say one thing ahead of time is that we won't be using colliders to approximate the floor of this scene. The way we're going to be working with colliders is we're not going to be using the standard physics system. We're going to be using the colliders and detecting collisions manually. So I'm just going to be adding colliders for the wall geometry here and for the boxes, but not for the floor. That will not be necessary. So let's get started at adding colliders to our project. So I'm going to start by creating a new game object in the scene. I'm going to move up here to the File menu and choose Game Object and create Empty, or I could press Ctrl-Shift-N on the keyboard, and that creates a new game object which you can see here in the hierarchy panel. Again, it's created it at this world position here, and I don't want that. I want to put this at the world origin, so I can choose the cog icon, and from the menu I'm going to choose Reset, and that resets it to the world origin. You can see here it's represented by this gizmo. I'm going to name this object colliders, like so, and you can see the name here listed in the hierarchy panel. And I'm going to be adding some new game objects beneath this as children, and these are going to contain the colliders we'll add to the level. So I'm going to press Ctrl-Shift-N again to add another new object, and I'm just going to parent it to this collider object here. Select this game object and just scroll around until we can find out where it is. Okay, so I'm going to put the collider for a wall piece in this area here. So about there, let's just raise it up here. And I'm going to add a collider component to this. So I'm going to choose from the File menu here, Component Physics. And I'm going to add a box collider. And you can see now that's been added in the scene. You can see it outlined by these green outlines here. So we've added a box collider. And if that's not visible for you, make sure that it's enabled here, box collider, from that gizmos drop down in the scene viewport. Make sure you have a tick there in box collider so that you can see that in the viewport. If it's not ticked, you won't see them at all, so make sure that's enabled. So we have this box collider, and I'm going to just adjust the size here. So I'm going to adjust, for example, its height to maybe something like that. It doesn't matter that it's a little bit larger than we need. That's absolutely fine. So let's just increase this just a little bit. I'm going to switch to the top viewport, switch to an orthographic view, and just increase the size here to something like this. The Z here to something like that. So now we've approximated the collision data for this whole corner of the level. And I really want to sort of repeat this procedure for the other sides. So I'm going to select this, press Ctrl D on the keyboard to duplicate that and move it over to this side. And again, let's just maximize the viewport here. I'm going to press Ctrl D and bring that down to this side here. And again, Ctrl D to bring that over here. And for these endpoints, if I just come out of the main viewport here and I choose the colliders, you can see all four are now selected. What I want to do again is to duplicate these and add them to the ends here. So one at the end here, one here, one here, and one here. So let's press Ctrl D to duplicate that, bring it in here, and just raise it up to around about there. Again, Ctrl D, bring that down here. Ctrl D again, let's just bring this over to this side and arrange it about there. And again, Ctrl D finally to bring this one over to this side. Now if I select the parent object, the colliders parent, you can see all of the colliders in the scene. And that's looking pretty good. We now have colliders around all of the walls. And I also want to add a collider to the crate object. So let's just go back to the scene here, switch to a perspective view, select this box here in the viewport. Again, notice it doesn't have a collider component attached automatically. We need to add one. So I'm going to move up here to the File menu, choose Component, Physics, and add a box collider component. And it quite nicely sizes this box collider automatically to the mesh to completely contain it and act as a bounding box. So this box collider for the crate here is already sized to exactly the size that we need. And in doing that, I've now added colliders to the scene geometry and the box geometry. We're now ready to move on. So in this movie, I want to consider the general logic that our collision detection is going to take, because we're going to be testing for collisions manually as opposed to relying on the Unity physics system to do it for us. So let's take a look at how exactly the logic is going to work. Let me just select the player character in the hierarchy panel and maximize the game view. Now with the player character, we know that when he moves, or when she moves rather, that she moves in discrete increments. So for example, right now the player character is standing there, but if we walk forwards, we know that we're going to be walking forwards by one tile, at least one tile. So that's 2 units in this direction. This means that when the player presses forwards, we know for sure that the player is going to walk forwards by one tile. And this really offers the key for our collision detection. Because what we want to do is, for example, let's say the player turns and faces the wall. What we want to do is to say, okay, so you want to walk forwards, do you? Right, well, what's in the next space? Let's take, for example, a point in space that's ahead of us on the next space here. And we want to say, okay, if I just select the colliders here, we want to say, okay, well, if the point on the next space is inside a collider, then we can't walk there because it is blocked off. It's marked by this collider and we can't walk there. But of course the player may also walk forwards and there might be a crate there. Now in that case the crate does have a collider, but we want to really test and say, okay, is this a crate? If it is a crate, that means we can push it. But things are not quite so simple, because though the player can push this crate, they can only do it because there's an empty space behind it. If there was another crate here, for example, the player would not be able to push this because they can't push 2 crates at once. They can only push 1 crate at a time. So we need to detect collisions not just for the next space, but also for 2 spaces ahead to see what kind of space is behind a crate if we come across a crate. So the first kind of functionality that we need to implement for collision detection is testing for points. We want to be able to pick up any point in the scene, any point expressed as a vector, an x, y, and z component, and we want to say, okay, is this point intersecting a collider anywhere? Is this point inside a collider? And we want to get a straightforward answer of yes or no. If, for example, we know that a point is here inside a collider, then we know that the player cannot walk there. So we're going to really start by implementing point testing with colliders. And we're going to be getting started with that next. So now I'm here in MonoDevelop and I want to show you the functionality that I've added for testing points with colliders in the scene to determine the kind of space that we are on. You'll see that it all begins here really with line 13, where we have public enum space state, and 3 states are defined. They are empty, crate, and collider, and these determine the kind of states that any space can be in. For example, let me just minimize MonoDevelop and bring up the scene here. For example, if we take this space here, well, we know that this space is empty. It's empty because we can walk there and there's no crate on the space. So the space is empty. This space here, for example, it is a valid space. It means that we could walk on it if there were no crate there, but it just so happens that right now there is a crate here. So the state of this space is crate. But then we also have the kind of space that's way out here behind the walls. Now this space is a collider space. It means that you can't push a crate onto there and you can't even walk there at all. There's no way that the player can ever reach this area. So these are the 3 states of any space in the level, and they are described using this space state variable here. Now, of course, I've also coded the point testing functionality further down in this source file using the point state function, and effectively it accepts any vector3 point in the scene and it tests that point to see what kind of space that we are on, and then the output value is a space state description of the space that is defined by this point. So let's see how the point state function works. Now it starts by using a for each loop to cycle through all of the collider components in the scene. We have a collider C in the array colliders. Now let's just scroll up to the top of the class and you will see that I've added a private array variable here of colliders, which is initialized to null, meaning that it begins completely empty. And in the start function at line 67, we say colliders equals object.findObjects of type collider. And what this will do, what this single statement will do, is populate the colliders array with all of the colliders in the scene. That includes the collider attached to the crate. So let me just minimize MonoDevelop and back in the scene here. If I scroll up and select the colliders object, it will include all of these colliders and also the collider on the box mesh. Now to prove this, we can do that easily. I can just move up here and change this variable, the colliders array, from private to public so that we can see it in the object inspector. Let me just move over, select the player character, and here for the player controller component, you can see the colliders variable here is currently in the editor set to size 0. But if I press play on the toolbar to begin playback of the level, you can see that it's automatically populated with 9 different elements. And these are all the colliders in the scene. Element 0, for example, if I select that, that is the crate mesh. And again, these other remaining colliders are for the wall objects that we created previously. So let me just stop playback, switch back to MonoDevelop, change this from public to private, press Ctrl S on the keyboard to save those changes, and scroll back down to the point state function. So we cycle through all of the colliders in the scene, and then what we do is we use the cbounds.contains function, testing it with the point here to determine whether the point intersects any of the colliders in the scene. If the point that we've specified does intersect a collider, then it could be a crate or it could be a wall. We need to test which one it is. So here we're using tags, compare tag, to determine what kind of object the collider is attached to. If this object is marked or tagged as a crate, and I'll show you tags in just a moment, then that means this space contains a crate. If, however, the collider is not associated with a crate, then it means that it must be a wall. So we return space state collider. But of course, if there was no intersection at all with a collider, if it wasn't a crate or a wall, then it must be an empty space. So it's important for this function to work properly that all of the crates in the level are tagged with the crate tag. And we can do that quite easily. Let me just minimize MonoDevelop and select this crate in the scene. You can see that I've already tagged it up here as crate. I just click in this tag field and I select crate. If you don't have the crate tag specified, you can add a new tag. Just click in that field, move down to the bottom, choose add tag, and then you can add your tag in here. But right now I have tagged this crate here with the crate tag, and that will allow the point state function to work correctly. So that's the basics of testing for points with colliders, but there's still more work to do. In the preceding movie, we coded point state functionality to check a point against a collider, and that is just simply one part of the movement mechanics that we are developing for the player. There is still more to do. In particular, we need to implement validation for player movement. And let me just show you what I mean by that. Because right now, although we have the ability to test for any point in the level to see which kind of tile it's on, we still need to have functionality that uses that point testing to work out whether or not the player is allowed to move forwards into a particular space. Right now, the player is standing here looking forwards, and the question still remains as to whether or not the player can move there. So for example, right now, if the player were standing back here and were to press forwards, we would use the point testing functionality to test for this point here, we would find in fact that the space was empty, and so the player could move forwards into that space. Again, if the player was turned to face in this direction here against the wall, and they were to press the forwards key, the W key on the keyboard, then we would not want to allow them to walk forwards, because the point in the next space would be inside a collider, and that would mean that the player couldn't move there. So we want to just undo those changes there. And finally, we have this case here with a box where the player can move forwards. We know that there's a box on this space. In this case, we need to also validate the space behind, because if there is a wall there, or if there is another crate there, then the player cannot move forwards and push this crate. But if there is an empty space there, then the player can move forwards and push this box with them. So to handle this validation for movement, I need to code a new function, and I'll show you that by returning to monodevelop. If I return to monodevelop, you can see that I've created a validate walk function, and it returns a type of move type, which we've seen before. It's the enumeration here that specifies whether the player is walking or pushing or is standing idle. So it will return the movement type that is allowed for validating the current movement. So how does this work? Well, first of all, it uses this value here for dest pos, and that gets the position, or a vector position, for the next space that is forwards in front of the player. So it uses the player's forward direction vector to determine what the next space is, and it gets that represented as a point. And then there's the double dest point, which takes the player's position and gets a point that is 2 spaces away. We will need to get this to test whether or not a crate can be pushed into an empty space. We then determine the status of the next space by using the point state function that we have coded and passing it the destination point here to determine whether the next space is empty, contains a crate, or is a wall. And we do the same procedure here for the space that is 2 spaces away from the user. We then move down and we say, okay, so if the next space is empty, then we can allow a walk there, and we return a type of move type walk. If the next space has a crate and the space behind the crate is empty, then we can push the box, and so we return that type. In all other cases where perhaps there are 2 crates stacked up together, or there is a crate against a wall, or the next space is simply a collider space, we return a type of move type idle, meaning that the player cannot move forwards at all. Movement is forbidden, even if the player is pressing the forwards key on the keyboard. We simply cannot move to that space. This validate walk function is integrated with our handle input function, which we have seen before. Here we have the functionality to code the rotation for the player. But if you take a look at the player movement, particularly the movement forwards, we call on the validate walk function to check whether movement forwards is allowed. And if it is, we then allow walking forwards or pushing the box forwards. So I'm just going to minimize monodevelop and test out this functionality now. I'm going to press the play button on the toolbar. Actually, no, I'm not. I'm going to exit this, switch out of the scene tab. I need to be in the game tab. That's important. Always remember to do that. So I'm going to switch to the game tab, maximize the viewport, press play on the toolbar, and now you'll see we can rotate around. I press W on the keyboard and I can't walk through that wall. It's blocking me even though I'm pressing forwards. Again, I can walk forwards and I'm being blocked this way, and again I turn here and walk forwards, I'm being blocked again, and that's because we put those colliders behind the wall. So our point state function is at work. What about in the case of a crate? You notice here we've got a crate, 1 crate, and there's no crate behind it, so I should be able to push this, and indeed I can. I can keep on pushing it, and notice that now I cannot push it through the wall. What about the case of 2 of these crates? Well, we can easily just sort of arrange that scenario. I'm just going to select this crate, press Ctrl D to duplicate that, and just move a crate behind it. And now press play on the toolbar, and I walk forwards, and I'm not allowed to move this crate now because there's another crate behind it. So the movement validation is now working excellently. But there is a problem. There is still one problem that remains, or an aesthetic problem that remains, and we're going to be considering that next.